Stainless steel drilling failure is not random, it's not bad luck, it's not operator error in the simple sense. In engineering reality, drilling failure is always a system problem. Material, tool, heat, and mechanics interacting in the wrong way. Today, we break down the 3 fundamental root causes of stainless steel drilling failure from an engineering perspective. No sales. No product promotion, only physics, metallurgy, and mechanical logic. Stainless steel is not difficult because it is hard. It is difficult because it is structurally sensitive to heat and deformation. Most failures happen not because of insufficient force, but because of incorrect energy control, heat, friction, work hardening, chip evacuation, material phase change. These are not workshop problems, these are engineering system problems. Stainless steel is highly sensitive to cold working. When drilling pressure is insufficient or rotational speed is mismatched, the surface does not cut. It deforms plastically first. This deformation causes work hardening. The material becomes harder, more brittle, more resistant to cutting, more heat sensitive. Once work hardening starts, cutting efficiency drops, friction increases, temperature rises, drill wear accelerates. Failure becomes inevitable. Engineering principle: if stainless steel is not cut cleanly on first contact, it will transform into a harder material layer that resists all subsequent drilling. Failure starts before the drill bit breaks. Heat is not a byproduct, heat is a control variable. Stainless steel has low thermal conductivity. Heat does not dissipate, it accumulates at the cutting zone. This causes loss of drill hardness, microstructural change in material, edge softening, surface glazing, chip welding, friction amplification. At a critical temperature threshold, cutting becomes rubbing, rubbing becomes melting, melting becomes seizure. This is why drilling suddenly locks up, not because torque is too high, but because thermal balance collapses. Engineering reality: once thermal equilibrium is lost, mechanical failure becomes unavoidable. This includes incorrect drill geometry, wrong cutting angle, inadequate hardness gradient, poor chip evacuation design, improper feed-to-speed ratio, structural vibration, unstable contact mechanics. Drilling is not just penetration. It is controlled material removal. If chip flow is blocked, heat spikes, friction multiplies, pressure concentrates, tool stress localizes. This creates micro-cracking, edge chipping, sudden breakage, unpredictable failure patterns. Engineering truth: failure does not happen at the drill tip. It happens in the system design logic. Stainless steel drilling failure is not caused by one factor. It is the interaction of work hardening, thermal accumulation, mechanical mismatch. This is a closed-loop failure system. Deformation, heat, hardening, friction, failure. Break the loop and drilling stabilizes. Ignore the loop and failure repeats. Stainless steel drilling is not a strength problem. It is not a torque problem. It is not a pressure problem. It is an energy control problem. If you control heat, deformation, friction, chip flow, structural stability, drilling becomes predictable, repeatable, controllable. That's engineering, not trial and error. Ending line: failure is not random, failure is structural, and structure can always be engineered.